I'm going to attempt to simulate 4.5 billion years in my room. All of this because I ask myself, how did life conquer Earth? Where do we come from? To answer these questions, I built a tank with 4 zones: deep sea, reef, coastal area and lush forest. Each zone highlights a specific step in nature's evolution with its according time frame. Of course, most of the earliest creatures have long gone extinct, so I replaced them with animals and plants we find today. Because there are still organisms that move like, are built like, or have barely even changed from their early ancestors. With their help, I can show adaptations and survival mechanisms you have never seen before. This channel brings creatures, stories and miniature worlds together like no other channel on YouTube. So make sure to subscribe, more is coming. Now, let's go back 4.6 billion years to the Earth during the Hadean Eon.
Life's a coat of many colors. It is never black and
A very different looking Earth. A hellscape before life. Its surface one vast magma ocean.
the dark without the light.
Eventually our planet's crust solidifies and jagged cliffs take shape. Meanwhile, massive volcanoes and cooling lava release columns of steam and toxic gases into the sky. Our young Earth forged in fire.
Breaking the fire. Been breaking the fire. I just been breaking the fire.
When finally the surface temperature dips below water's boiling point, steam condenses into clouds. And for the next millions of years, acidic rain falls. This primordial rain fills the basins to create our first oceans. The leading scientific theory is that deep in the early oceans, hydrothermal vents sparked the chemistry that set life in motion. In the late Hadean, hot mineral-rich water mixing with cold seawater would form simple building blocks: amino acids, fatty acids and even fragments of RNA. Over a long period of time and just the right conditions, tiny bubbles called protocells may have trapped these chemical systems inside. By the way, if you're new to the channel, I create almost all the footage you see from scratch. Like the Hadean Earth we just saw, that's really 2 balloons and some paint. Practical effects take planning and effort, but I enjoy creating unique visuals. So let me know if you support these kinds of handmade shots by leaving a like. After the Hadean, we reach the Archean Eon that lasts from 4 to 2.5 billion years ago. Some protocells gain the ability to copy themselves through self-replicating molecules like RNA and early forms of DNA, gradually turning into the first true reproductive cells. Those true cells are the ancestors of all life we know today. They are considered the first living beings on Earth and kickstart evolution. Before we continue on our journey through evolution, we have to understand this term first. How exactly is modern biological evolution defined? Evolution is the change in heritable traits of a population over many generations. In other words, parents pass information, mainly via DNA, to their offspring, but each new generation isn't an exact copy. Random mechanisms like genetic drift, mutations, or non-random processes like natural selection create changes that shift the traits seen in a population. Natural selection is a powerful engine driving evolution. I remember my middle school teacher explained natural selection with this example from northern England: the peppered moth. Before the Industrial Revolution, most were light-speckled and blended in with the local birch trees. When coal-burning factories began spewing out soot, trees became covered with dark particles during the mid to late 1800s. Bright moths were easily spotted and eaten by birds, while a rare dark mutation was better camouflaged and survived in larger numbers. As a result, dark moths became the majority, a clear case of natural selection. Then, after air quality laws cleaned up the pollution starting in the 1950s, the trees returned to their natural bright coloration, and over time, the moth population did so as well. We understand now how traits in animals can change over time. The peppered moth has changed coloration not once but twice in about 100 years. We can imagine how simple cells become more complex over billions of years through evolution. So, still during the Archean Eon, some of the simple cells evolve into cyanobacteria, also called blue-green algae. They gain the ability to split water using sunlight, releasing oxygen as a byproduct. For hundreds of millions of years, that oxygen was absorbed by Earth's oceans and rocks. But then, during the Proterozoic Eon, and about 2.4 billion years ago, oxygen finally begins to accumulate in the atmosphere. This triggers the Great Oxidation Event, which permanently transforms Earth's environment. Around 2 billion years ago, we can see how some cells begin to evolve greater complexity. A key step was one cell engulfing another, giving rise to eukaryotic cells. Cells now have a nucleus enclosed by a membrane and other organelles. Some eukaryotes begin living in colonies, cooperating more closely over time. They form carpets of cells that can even be seen with the naked eye. By around 1.2 billion years ago, the cells in these colonies become so interdependent, they can no longer survive alone. They begin to specialize. Some take on movement, others focus on reproduction. We can see how unicellular life step by step develops into multicellular life. Most living organisms are still bacteria, algae, and a handful of simple animals. But with multicellularity now established, the path is open for a wide variety of new organisms to evolve. We reach the Phanerozoic Eon, and because things start to progress faster and faster, we divide the time span from eons lasting hundreds of millions to billions of years to periods lasting tens of millions of years. In this video we are taking a closer look at the first 6 periods, also called the Paleozoic era. From the deep ocean we move on to the reef and witness one of the most remarkable events in Earth's history. The Cambrian explosion, about 540 million years ago. We get a sudden burst of life diversifying and many new body plans emerge. Eyes for vision, hard shells for protection, jointed legs for movement, and all appear in various forms. This is a selection of animal groups with some representatives during the Cambrian for us to get a better idea what the animals look like during this time. Let's inspect 3 of those newcomers. Many animal groups have already evolved eggs as part of their reproductive cycle. But from these hatch algae-eating mollusks. Snails. These snails have specialized mouth parts to scrape algae from rocks. fueling a new kind of ecological interaction: grazing. The most iconic animals of the Cambrian seas are trilobites. Unfortunately long extinct, I choose triops to represent their legacy. These ancient crustaceans have barely changed in millions of years, earning them the nickname living fossils. Just like trilobites, triops have segmented bodies, compound eyes, and armored exoskeletons, traits that echo their distant evolutionary cousins. Triops also lay eggs which can survive extreme drought and remain dormant for years, only hatching when water returns. From there they grow quickly and reach the adult stage after a few weeks. This one is not hurt, but in order to grow they mold their exoskeleton, and it's trying to shake it off. Despite their fossil look, they are surprisingly relatable. They dig, swim, flip upside down while feeding, and sometimes for no apparent reason, slap others in their way. During this age, countless shells and exoskeletons settle on the seafloor and slowly turn to stone. Their remains can still be found today, preserved as fossils like this trilobite. The last example from this period appears about 525 million years ago. These are the first chordates, simple creatures with a notochord, essentially a very early version of a backbone. These creatures become the blueprint for all future vertebrates, for example us. To picture them, let's look at a ghost catfish. It has a similar shape, but what's more fascinating is within its clear frame we still see the same spine. The ancient chordate design carried forward for over 500 million years. Yet, unlike the agnathans, the catfish also bears some newer upgrades of later fish: jaws, paired fins, and bones, to name a few. Still, this fish is mesmerizing. An even higher species diversification than in the Cambrian explosion happens in the Ordovician period. Existing animal groups explode in number and complexity. Early reefs are built by corals and sponges. These organisms may not look like it, but they are animals, not plants. Aquatic plants come much later, evolving back to the water after their ancestors have conquered the land. Speaking of which, let's make a quick detour to the surface, because here we find the first land plants, small and low to the ground. Liverworts and mosses take the stage. They reproduce via spores, which are single cells capable of growing into a new plant. At the end of the Ordovician period, we have an absolute devastating catastrophe happening. The first of the big 5 mass extinctions in our history. Global cooling causes a sudden ice age, sea and oxygen levels drop. An estimated 85% of marine species went extinct. So, Was all that Ordovician diversification for nothing? No, not at all, and here's why. Mass extinctions prune the tree of life, but don't cut it down. The lineages that survived carried forward millions of years of evolutionary progress. These heroic survivors set the stage for even more complex life in later periods. Once the climate stabilizes, we arrive at the Silurian period, 444 million years ago. Life comes back and brings new inventions. Some of the plants are vascular now, meaning they have stems with internal tubes to move water. These early plants begin forming Earth's first soils by gradually building up layers upon layers of organic material over the barren rock below. They also draw carbon dioxide out of the atmosphere and release oxygen, laying the groundwork for modern climate regulation and nutrient cycling. In this period, the first arthropods are making the bold transition from sea to land. These pioneers include millipede-like creatures, early spider relatives, and ancient scorpions. But what did that transition look like? A great modern-day example comes from a coastal isopod known as Ligia. Let's find out why. The gill-like structures under their abdomen lets them breathe underwater and on land. This kind of transitional respiratory systems resemble the ones early arthropods probably had. Scuttling across rocks, these animals need to stay close to water as their gills must remain moist to function. Without constant humidity or contact with water, they quickly risk drying out and suffocating. But true terrestrial life required a new kind of adaptation, breathing dry air directly. Millipedes are among the oldest land animals to achieve that. They breathe through trachea, a network of tiny tubes that carry oxygen straight into their body. No gills, no water required. This difference, moisture-bound gills versus air-filled tubes, marks one of the most important evolutionary divides in the history of life on Earth. Some of the terrestrial arthropods like springtails and isopods further improve the nutrient cycle by digesting fallen plant material. They transform decay into fertility, returning nutrients to the soil and making way for the next generation of plants rooting here. Meanwhile, for the first time in history, one of evolution's most powerful inventions appears. Jaws. Jaws evolved from the skeletal rods that once supported gill slits. With jaws, animals can bite, tear, and crush. Suddenly, predators have weapons, herbivores have tools to chew. The ecosystem is forever changed. A world of hunters, grazers, and rivals with teeth. One of those predator types we still know today. Sharks. Or in this case, a fish that's called Bala shark because of its fins and body shape. And by the way, it is true, sharks, or at least their early versions, are older than trees. 419 million years ago, we arrive at the Devonian period, which also has the nickname the Age of Fishes. And we can see why. It is a time of extraordinary diversification and dominance of fish in Earth's ecosystems. Even their jaws come in all shapes and sizes by now. fish become the top predators in rivers, lakes and oceans. Some grow massive, up to 10 meters long, while others stand out for very different reasons. Because about 45 million years later, something special happens. The first vertebrates begin to transition from water to land. The Tiktaalik is significant because it represents a key evolutionary step between fish and the first land-walking tetrapods. With fin bones like protolimbs, it shows how vertebrates begin taking their first steps onto land. It likely moved awkwardly on land, like a blennyfish, which is a modern-day example of water-to-land transition. Time to prepare the water for those blennies. They are quite lively and have a lot of personality. They kinda look like they're awkwardly waiting for someone to end their conversation so they can ask a question. Their eyes are situated high up on their heads, so they have a good overview when they stick their head out of the water. But the most interesting part is when they make the jump onto land. Most fish gills collapse and dry out on land, but amphibious blennies have stiffened gill structures and moisture-retaining tissues, so they can keep exchanging gases in air. They're literally breathing with their gills, just using them differently than underwater. They can stay out of the water up to several hours at a time, pushing the boundaries between sea and land. They even have a pair of extra fin-like legs. We are witnessing a transition, a living experiment, evolution mid-step. But eventually, they need to go back into water. Meanwhile on land, another organism is incredibly successful. But it's not fish. It's not even in the animal kingdom. Until now, the vegetation was still growing low to the ground, but we have a crazy new invention. Trees. Nowadays, this doesn't sound too crazy, but we modern humans are spoiled with literal millions of different plant and animal species. Back then, however, it was the latest fashion for plants to grow higher and higher in an attempt to reach more sunlight than their competitors. But once again, the diversification of the Devonian era is with only 60 million years short-lived. What caused the late Devonian mass extinction is still debated, but it is one of the big 5 mass extinctions, this time culling up to 75% of marine species. It hit reef-building organisms, armored fish and many trilobites especially hard. We arrive at the Carboniferous period that started 359 million years ago. And the surviving species turn into oversized nightmares. This is the age of giant insects. Remember the regular-sized isopods that have been around for a while now? Their massive cousins have arrived. This is the kind of size we are dealing with now. What are those armored spheres exactly? They look like a regular isopod that fell into a cauldron of growth hormones as a child. Although they look like the smaller now panicking isopods, they are actually millipedes, just like the rusty millipede. One way to tell is they have twice as much legs per body segment. They are also pretty water tolerant. They don't even mind going for a quick skinny dip. Their signature move is to roll up in a nearly impenetrable ball to be safe against predators or hiking accidents. Some giant insects even gain the ability to fly. The fulvous forest skimmer is a close modern example of what the extinct giant dragonflies were like. Both share the same basic three-part body plan: head, thorax and abdomen. The large mobile head has huge compound eyes, giving nearly 360 degrees vision. They also both are predatory insects and have two pairs of long wings with a dense network of veins, allowing hovering, backward flight and sudden turns. But how are these monsters able to grow that big? The reason is high oxygen levels. The Carboniferous has the highest oxygen levels in Earth's history, up to 35%, compared to today it's around 21%. Arthropods don't have lungs like us. This dragonfly takes in air through holes next to its wings. From there it flows through tiny tubes where oxygen just spreads or diffuses directly into their body. The more oxygen in the air, the bigger the insects can grow. The first seed plants already appeared in the Devonian, but it's during the Carboniferous that they become widespread. While spore-bearing plants still thrive, seeds offer new advantages, especially in drier environments. During this time, seeds begin to diversify in form. Some with thick protective shells, others with elaborate structures to help their dispersal. In the future, evolution will come up with very different shapes and builds for seeds. Some will develop sweet, fleshy coatings that become fruits and berries, while others will harden into tough shells we now know as nuts. Not all organisms change drastically over time. If a body plan proves highly successful, it can remain almost unchanged for millions of years. For example, there is fossil evidence of our next creature dating back to the Carboniferous. This is a whip scorpion. It has this name because of its whip-like tail, which is covered in fine sensory hairs that detect vibrations, air currents and chemical cues. The tail helps it navigate in the dark, since whip scorpions are mostly nocturnal. Unlike true scorpions, it's not venomous, but it can defend itself instead by spraying acidic acid, a vinegar-like liquid, from glands near the tail. so other animals better keep their distance. But regular viewers know that the animals on my channel aren't big on respecting personal space. The Carboniferous period produced many more giant arthropods. But towards the end of this period, an invention happened that let reptiles replace the dominance of the arthropods. The amniotic egg. An egg with a hard shell that doesn't dry out and can be laid far away from water. This opens the path for vertebrates to fully colonize land. Before the rise of reptiles, I want to shout out my premium Patreon members. Your support directly helps me to create new videos. If you want to join, the link is below. Our final period for this video is called the Permian period. It started 299 million years ago. Reptiles and amphibians really take off now. Some of them are the first truly massive land-living animals. I would have loved to show you more animals representing this period, but unfortunately I ran into shipping problems. So sorry for that. But I have one last animal I'd like to show you. This species is special because it provides one of the clearest living examples of a major body plan shift mid-step. Let me explain. This is the Lygosoma. And at first glance you would think it is a snake. But upon closer inspection you can see it has 4 tiny legs. Its ancestors had larger, fully developed legs, but as the Lygosoma is a lizard hunting for insects in leaf litter, wide shoulders and large legs tend to get stuck. That's why when moving through tight spaces it presses its legs tight against its body. So on average, the Lygosomas with smaller limbs get stuck less, which means small leg Lygosomas are more successful hunters, which means they survive more and can reproduce, which means that if we go on like this, we can see how this unfolds a transition from a lizard to a snake-like body plan, and we are looking at the in-between stage. And another fascinating part is, this doesn't happen just with this species in one part of the world, but multiple skink species independently and scattered across the world evolve in this way. So if we want to look at proof of evolution, we can actually go outside and find it. Although to see the actual transition you might need to wait for a couple of million years. The Permian period was the last period of the Paleozoic era. A time of great evolutionary achievements, but also it ends in another one of the big 5 extinction events. And this one is the largest extinction event in Earth's history. Now it is time to bring an end to this terrarium, so for what comes next I carefully take out all the animals. What caused each mass extinction is still debated. At the end of the Permian, it was probably volcanic eruptions and climate change. But one fan favorite idea is a giant meteor, which makes for a spectacular visual. I'm a bit sad to see the end of this terrarium, and you might be too. But if extinction events taught us anything, it's that the end of one thing is the beginning of something new. And this might just set the stage for another video. After all, there's still the rise of birds, dinosaurs and mammals, a messy evolution leading all the way until some of them start walking upright. One thing we do know for sure though, is how that story ends. It ends with you watching this very video. In the reflection of your black screen, you see the latest iteration of 3.5 billion years of evolution. A goofy-looking hairless monkey staring back, wondering where to go from here. Don't worry, nature's just trying a new variation of DNA with you. Whether you turn out wildly successful or a miserable failure in life, you're still helping the grand experiment we call evolution to progress. So, you might as well enjoy the ride.